And good morning. Hello, everyone. I should add that while I started the show and hosted Planetary Radio for 20 years, it is now hosted by my absolutely fantastic colleague, Sarah Alamed, who is my choice, even though she had to beat out 300 people to take over the show, and she's doing an outstanding job. I'm now the, what do they call me? Senior Communications Advisor for the Planetary Society. I've been saying, be still my heart, because of this panel. And I will introduce them one at a time. Each of them will have a brief presentation to make to you. But just to open things up, how many of you have seen the 1950s movie, The Conquest of Space? It's a classic. It was based on the Willy Ley and Chesley Bonestell book of the same name, The Conquest of Space. I've been thinking a lot about what a comically over-the-top phrase that is. But to attempt to understand the cosmos, to answer those two great questions, where do we come from and are we alone? Which we'll be hearing about a lot today. Is there a greater quest than that, or is there one with a better return on investment? Yet, every few years, our leaders lose sight of the value of science and exploration, and it would seem that we have entered perhaps the greatest period of that challenge in our nation's history. And that's why I'm really so honored to help open this year's Humans to the Moon and Mars Summit, and to welcome these four superb scientists. So as I said, we're going to go right down the line here, beginning with Jim Green, Dr. James Green, the former chief scientist of NASA, and for a lot longer before that, the leader of the Division of Planetary Sciences at the agency. Jim is co-author of the brand new, and I can tell you from personal experience, spectacularly beautiful book, Mars Photographs from the NASA Archives, which has just sold out its first printing, at least in the US. So hopefully there'll be more available soon. And he also chairs the Explore Mars Board of Advisors. Jim, help us get started.
Well, thank you very much, Matt. What I'd like to do is sort of set the context of why we need a scientist to be able to talk about what we do, get the knowledge out. And it's because of the federal funding that we receive that allows us to do these spectacular things. Well, the president has issued what was called the skinny budget. And in this particular budget, there is a mark for reductions, not only in earth science, but in the space sciences. And this reduction is quite large. It reduces Planetary by $3+ billion out of the $7.8 billion that it currently has. It's important to note that the science aspect of what NASA does is really less than 0.5% of the total discretionary budget that is given by the federal government. And the marvelous things that we do with this, we'll talk about, of course, by the wonderful panel that's here. So this is a graphic that gives us a really great overview as to what's in the skinny budget. Not a lot of direction, but some tough things to take. SMD will take a $3.4 billion decrease. That's 47% of the budget. And it's broken up in two pieces. One is the earth science piece, which is a reduction of $1.2 billion, with direction on cutting back or eliminating funding for lower priority climate missions. In the space science part of the budget, space science should be thought of as those four divisions. That's astrophysics, heliophysics, planetary science, and the biological and physical science division. That has a reduction of $2.3 billion with direction on canceling Mars sample return. Now, what's in these budgets? As a division director, I can tell you we bin things in certain categories that make a lot of sense. there's mission elements. Now, the mission elements, there are several. One is a strategic mission for which the division is responsible for. These are large missions, typically above $1 billion or even higher. These strategic missions then push the limits of technology, are designed to really step out and make some spectacular discoveries, and they all do. They've been all tremendously successful. Right now, the strategic missions that are being considered were Mars Sample Return, Nancy Grace Roman Space Telescope. Landsat and its follow-ons would also be called strategic. Those are designed at the division level and promoted. Then there's a series of competed missions, allowing the community to go after some really well-focused science objectives that are delineated in the decadals. Now, once you have missions up, and SMD has probably at least 100 operating spacecraft in the solar system, orbiting the Earth too. These operating missions you have to be able to fund. You know, they're in the process of being in their prime mission or their extended missions for which they're going after new and important science objectives. Those are important. And then, of course, there's a variety of instruments on other agency spacecraft. And this allows our scientists to connect with our international partners. So NASA as a mission agency has these kind of opportunities associated with it. Now, when the data comes in, flows into the archive, then other scientists that aren't directly associated with the mission can propose to do increased analysis, and that has just been an enormous boon. For instance, today, more science papers are coming out of the Hubble archive than are coming out in the prime mission, where you get time on the telescope, make your observation, write your paper. So these long-term archives are incredibly important. That feeds into the research analysis portion of the budget, and that's about 10 to 25% of a division's budget. Then there's national needs, looking for NEOs, okay? This is very important in terms of knowing what's out there, what are the potential impacts, and do everything from civil defense to even testing things like moving a NEO, which is done recently with the DART mission. And of course, there's other things in that area which include cooperation with NOAA and also facilities that you have to fund. And then finally, there's a technology part of the budget. This is for instruments, this is for unique spacecraft capabilities that the division needs, such as radioisotope power for missions going to the outer planets and beyond, out into the interstellar medium. Now, the management principle NASA uses has to be understood in terms of how do you take a cut that's so large, how do you look at that portfolio and decide what are you going to cut, what are you going to keep? And each of the divisions really work hard to create a balance. Now there's a certain approach associated with it. If you're going to start cutting missions that haven't been launched yet, the basic principle that we talked about a lot at NASA headquarters is first in, is the next mission you have to cut. So this really hurts those missions that are in the development phase if they're not going to make it. And in planetary science in particular, that's incredibly difficult because we have windows we have to meet. And if you delay a mission, sometimes you then can't do the mission at all. So there are large portions of the budget that will have to be taken with these kind of rules in mind, and everyone looks at the decadals. So these are the decadals. And in these decadals, there are some decision rules. And they're all pretty consistent. Here's an example of decision rules. And in this set, you see you cut out the strategic missions or delay them. You reduce your competed missions. Those will be the ones that are currently in the process of being developed. And then you delay your competitions. And typically at the very end is research and analysis, because you have your community you have to support. And so this is also true in all the other decadals. There are certain associated rules for which saving the RNA program and keeping the community intact is the best approach. So in conclusion, there's going to be no new starts in strategic missions. That won't be possible. This is why Mars Sample Return, which would be that next big strategic mission, has been canceled. You're going to be canceling some competed missions. Last in, the last one you decided will be the first one out. You delay all newly competed missions because you don't have the money to fund them, even if you can make a selection. And then you have to somehow figure out how to shrink the national needs. So that has to be folded into this priority. So for the divisions, you've got operating costs like the operating missions. You want to be able to support as much of the community as you can through R&A. But the cuts are so deep, half the budget, that even reductions in those areas will be expected. So that makes it a very difficult environment that we're moving into. And so with that, what's happening with our science?
So we will hear more specifically about science, beginning with our other Jim G, James Garvin, Chief Scientist for the Goddard Space Flight Center. Also had that title for 4 years at headquarters, right, as the Chief Scientist for the Mars Science Program. It's largely due to you, I think, Jim, that we know exactly how tall Mount Olympus is and how deep Mariner Valley are, thanks to that MOLA laser altimeter. So within what, a few centimeters?
Oh, less than a meter.
Yeah, it'll do, I suppose. Jim, take us to the red planet.
Well, thanks, Matt and Jim, for setting me up. I'd like to look through the lens of the universe of science Jim was talking about, through the ways it's been funded by leaders like him, and focus on Mars, because we're really in a very special moment right now. We're looking at 50 years since we first had the audacity to ask, are we alone, through what we could read in the record of Mars, before we had ever landed on any other world robotically other than the moon. And we did that literally 50 years ago with Project Viking, and learned a lot in the intersection of the science we choose to do, but also the engineering masterpieces that allow us to do that. And that's the legacy that lives on in all these programs that you heard from Jim. So let me just remind you what we did. We went to Mars 50 years ago with our eyes wide open in the possibilities of a very Terra-centric world. And that red Mars we see is not the Mars under a veneer of dust, as you'll hear later. We also saw cycles of what I would call the Mars meteorological system and the climate that we didn't even know were existent. There's the frosty Mars. It happened on a Halloween, maybe. Not really. But at Viking 2, we saw this exchange of volatiles in Mars, and we realized the Mars atmosphere does amazing things every year. And so Project Viking emplaced our engineering and technology power onto Mars to open that frontier. And maybe we didn't know what we'd find, but we discovered the engineering boundary conditions to give us, I would say, the boldness to go after new things. And that set in motion a new Mars exploration program about 15 years later that culminated in many things. I only have a minute or two to talk, but I wanted to remind you, science comes in different flavors. Sometimes the science we measure, and in this case, the topography of the planet Mars in a geodetic framework good to a meter everywhere, gives us enabling powers. Before we had the mission of the Mars Orbiting Laser Altimeter, the knowledge of where to land on Mars, I always use the analogy of landing on a carrier deck with uncertainty at the level of 1,000 feet. I'm sure the great air flyers, the naval pilots, would probably not like to know that about the deck position on landing on a great carrier. But that was where we were before MOLA gave us Mars in 3D at the level where we could see the whole planet, figure out aspects of its interior, and also see magical things like the crater Korolev, seen there with a central mound of ice that rises above the rim of the crater. How does that happen? And these are some of the magical discoveries that a new technology that many said should not be done gave us the ability to see new things about our world that we've now been visiting and landing on successfully ever since that mission. We've also put in place the ability to do the recon for the future. And this is really important because the science questions require context. And you saw that in the workings of what Jim showed. And so we put in place, when we restructured Mars in around 2000, the idea that we would measure everything we could at all the scales that matter, including those that would enable sample return, and humans, crew, women and men going to Mars. And so the Mars Reconnaissance Orbiter, now 20 years in its life in space, has done many great things. I can't possibly describe the voluminous papers that have been done, but one thing it did was it mapped every square inch of Mars on a 6-meter digital image framework. That, for the price of literally a small B movie, gave us the ability to put what we do on Mars today into the context of landing safely, driving where we want to go for all of Mars. So now the trade space of where we can go is open to the eyes of where we want to go, thanks to that mission and also the higher resolution data sets. So the Mars Reconnaissance Orbiter is an example of producing science in the context of the engineering boundary conditions to let us go to Jezero Crater, Gale Crater, to imagine climbing Olympus Mons with those giant escarpments that are a harbinger of how Mars worked. So this is just part of the legacy of the program. So 50 years in, we've come a long way. And yes, the rocks of Mars seem to be staring at us with their glasses. They're in a view from Curiosity. But some of the discoveries, and you're going to hear about those from Jen and Danny in the next session, are really transforming how we look at the planet. Not from just, let's see what we get, but to not just following the water, but following the organics as indicators of what it might be like to be there, work there, live there, and return stuff from there. And that connects Mars deeper than just a one silicate rocky planet with a small atmosphere and a changing climate to the bigger cosmos that you'll hear about from John. So let me just remind you then the legacies we have. Petabytes of data that describe the planet from all the scales, covers of literally hundreds of prestigious journals that declare that science in the publication record and in other ways. These are just a sampler of some of my favorites. Please, there's many, many more by many other journals. But it just shows you the diversity of thinking in the science we've had in this Mars program. From organics to seeing fossil river deltas, to understanding the sapping that could occur on hillsides, to Mars in 3D. And so I leave you with a couple thoughts. I know my time is quick. One thing is, we know Mars is a dust world. Critical to its current evolution is its meteorology, if you will. And we see the dust storms on Earth, beautifully seen here from the International Space Station. The Mars dust space is still the nano-Mars we don't know. That'll be a key ingredient to looking to go there ourselves, to living and working there. And I'm reminded of this great little artist piece for Dust on Mars that just reminds us how even the artists have captured that unknown in this fabric and this quilt work. So I'll leave you with a couple thoughts. I think of Mars as we leave our planet and go back to the moon with Artemis as that doorway we will leap from. From that era, set up by these robotic missions we've been talking about, into a new era where Mars will connect beyond just going there ourselves, but through doorways to the bigger beyond. And I'd like to just show you a friend I brought with me. So here is 600 grams of Mars. The beauty of our program in science and engineering is to know that this is from Mars. From experiments that flew on Viking and Curiosity that are still working, to know that we have this artifact of another world delivered not by humanity, but by Mother Nature, is part of the magic of the exploration we do, to know that. This is probably more valuable than some of the great gems we like to wear ourselves, because it tells us about a history of another world. And our goals in Mars are to understand this and understand what we, with high level of informing, wanted to bring back. So Mars rocks. We're still there with those missions, those continuing missions, and we want to go back ourselves and with robotic emissaries to figure out what Mars still has left to tell us. So thank you, and let me turn it to Brittany.
Thank you, Jim. Well done. I'll tell you my story later about Alan Hill's 84001 that I got to hold a little fragment of with tweezers and gloves. We're going to continue on out across the solar system now. If you ever have trouble reaching Dr. Brittany Schmidt, it might be because she's a few thousand kilometers from the nearest cell tower. She's an associate professor in both the astronomy and earth and atmospheric sciences departments at Cornell University. Home campus, of course, of our founder, Carl Sagan, at the Planetary Society. Brittany, how many seasons have you spent now at either the top or bottom of our planet?
9 in the Antarctic and 4 in the Arctic, so just a few.
And why does she do this? Well, in part because it's her lab that has built and deploys IceFin, a robotic submersible whose descendants, I certainly hope, will one day descend down into the warm sub-ice oceans on worlds like Enceladus and Europa. I'm also very proud to say that she chairs the Space Policy and Advocacy Committee for the Planetary Society's Board of Directors. Brittany, it's all yours.
Thanks. It's a really an honor to be here today to talk to you about the solar system beyond Mars and its connection to the exploration of the Moon and Mars. So in these pictures I'm showing here are just some of the work that we've done, but we just represent only a couple of the programs that have been funded primarily through NASA's RNA programs, research and analysis. So in this particular slide, I'm showing you examples of science and technology that's co-funded. So programs through the astrobiology program that allow us to co-develop technology and deploy it here on Earth to test that technology and to get better science done by embedding engineers and scientists in the process. And that's exactly what we do here. So shown in these pictures here are our robot IceFin, which Matt just introduced, which is a technology development platform for future missions, hopefully to Europa. And while it was built by funds from NASA and universities, it actually has turned into being a big climate explorer for our own planet, participating in National Science Foundation research as well as international campaigns. So that's on the left side. So those are a few of the IceFin expeditions and some of the space missions that we've been able to inspire using our now understanding of how to explore the Earth, particularly in this rare place, hard to get to place underneath the ice. On the right-hand side is examples of, it turns out I actually do some Martian research, but it's also here in our backyard. And so this is Pingo Star, which is my favorite acronym ever. But it's an exploration of the Earth's permafrost using technologies that might be applicable to future human exploration. So here we're dragging things like ice-penetrating radars and resistivity mappers to search for ground ice in the poles of our own planet. So it's helping us to understand how these processes work here for the very first time, as well as proving technology. And as I mentioned, all of this isn't funded through a flagship mission. It's funded through NASA research and analysis grants, and often through logistics through National Science Foundation. So last year, I had the opportunity to sit and watch something I've worked on since I was a graduate student launch to space. So this is Europa Clipper, which is the work of tens of thousands of scientists across the United States at universities, as well as NASA centers. Europa Clipper launched in October and will finally arrive into Jupiter orbit in April of 2030, and then move on to a multi-year tour of the Jupiter system. It was a really cool experience. It's our next big flagship mission, and the first one ever dedicated to the exploration of an ocean world. And one of the most important, unfortunately, this background doesn't show the text that I had, because my background was black, but what I was showing was that the ice-penetrating radars that have been sent to Mars and are now on its way to Europa were built here first and tested in Antarctica in order to study the Earth's climate. So what does this look like? So we've got these beautiful places, Greenland and Antarctica, and if you're less familiar with some of the research that's done there besides the Earth's climate, there's actually a ton of Mars research done there in the Antarctic dry valleys, which is one of the closest environments on our planet to that of Mars. How that really works is that the National Science Foundation actually funds both science and logistics that go to Greenland and to Antarctica to do the science there. They fund all of our presence in Antarctica and most of the science presence in Greenland as well. NASA also has interest in that because we want to go to places like Europa and to Mars and to understand these environments. So NASA funds RNA programs, which you also can't see here. So this is P-STAR, Solar System Workings, Exobiology, Mars Fundamental Research. Those programs have funding that goes to the scientists. Then there's a co-funding and a logistical support that goes towards that work being done in Greenland and Antarctica. And so indeed, the interplay of these agencies also really matters in the fabric of science and in turn, the fabric of Mars exploration. In fact, most of the astronauts these days have been to Antarctica, or many of them. It's considered one of the great training grounds to work in these extreme environments. And so there's a whole bunch of interactions between these agencies that you might not be thinking about when you think of NASA and space exploration and humans going on to space. I want to highlight here that the National Science Foundation is also under extreme duress. This is just this year. This is before the budget cuts that we expect to come down, which are even more massive than those that NASA's facing. NASA's facing 24% top line. The NSF is facing at least 49%. We don't have the details on that. But I'm showing here this recent article from the New York Times that shows that the Office of Polar Programs has already spent only 22% of what it would spend in an average year this year. So that's before this budget cut. We've already cut science and logistics in Antarctica by 88%. What does that look like? Here's what we did when we wanted to go to the moon. We put a whole bunch of money into it. Right? And that trickled down. That actually did work, right? We funded all science because it's all interconnected, because all of these technologies and all of these innovative minds are the ones that will eventually bring us the technologies that we need. That's the backbone of our economy, the backbone of innovation in the United States, and a lot of it was born from the Apollo program. That's what we proposed to do there. Here we want to go to the moon, and now we want to go to Mars, an even grander challenge, and we're going to do it by cutting the budget. That should work out well. And here's the biggest lesson here is that the public supports this. So this is a recent Pew study that shows what people think NASA should be doing. At the top of that is monitoring asteroids to protect our own planet, monitoring parts of the Earth's climate system, and conducting basic scientific research. These are on the hit list during this budgetary crisis. So while we're hearing a lot about how we're going to direct science and engineering funding towards the moon and Mars, I just wanted to give you a picture of how we got to the moon and Mars in the first place and how we might think about doing that if we can get back to a budget reality that makes some kind of sense. Thanks.
Thank you, Brittany. All right, we're going to head even further out into the cosmos now by hearing from John Mather. He was named MVP when he shared the Nobel Prize for Physics in 2006, thanks to his cosmic background Explorer spacecraft and what it revealed about the bath of microwave radiation that we all live in that is the remnant of our universe's birth. John was also the senior project scientist for the James Webb Space Telescope from 1995 until just a couple of years ago, so, no big deal. John still serves as a senior astrophysicist at NASA Goddard. John?
Well, okay, thank you. I'm glad you're all here to think with us about what can we do and what may come next. I want to show you some stories about what we've already been able to do and what we're thinking about. So here is a picture of the great James Webb Space Telescope. The background in the picture has changed a little bit, but you see the great golden hexagon. It's 6.5 meters, about 21 feet across, and we did that. It's an international partnership between NASA, Europe, and Canada, and we did that. About 20,000 people it took to do that. So one of the most amazing collaborations that I can possibly imagine participating in, and I got the privilege of speaking about the science to all of you for a long time. So thank you to the public who supported this. It's one of our biggest science projects ever, and it's been massively successful. I won't be able to show you all that many of our results, but I want to tell you a few of them as we go along. So why do we do all these things? Well, where do we come from? It was already mentioned before. Well, astronomers have been working on this, and it's not only how do we study the Earth, but how do we get to that? Where did the Earth come from? Where did the sun come from? And here's the next question is, what do we, who are we? Well, that's not really my question to answer. Maybe philosophers will be able to answer that better. But we can, as astronomers, work on what is the cosmic history. We know about the expanding universe, which is mislabeled the Big Bang. And we've been working out a lot of the details of it, and we still haven't got it quite figured out because there's more to do. Biggest question that I've had, and I think many of us have had since childhood, was, are we alone? As Fermi asked, well, where are they? And why haven't they been visiting? So, well, some people think they have. But at any rate, astronomers can work on the evidence, and we're trying to figure that out. We have been able to locate thousands and thousands of planets around other stars, and I'll show you a little bit about how we do that. And we're learning something about them. So far, no other solar system just like ours has been turned up, but maybe they're there and we just can't tell yet. Is life a miracle? Well, people used to think so. And now we're beginning to make a little bit of progress on the chemistry, and the possibility of how it might have actually occurred here on Earth. Now, Darwin suggested maybe it happened in a nice little warm pond. Well, maybe, maybe not, but anyway, that's an idea. And people are working out the chemistry of how it might have happened. Well, how far can we go? Well, so far we've only thought of chemical engines that we can imagine, and solar electric propulsion, maybe the nuclear electric propulsion, and that cannot actually get us very far even in the solar system. It's a pretty big place we live in. So we put the Webb telescope 1.5 million kilometers away, which is only 0.01 of the distance to the sun. It seems like a long distance to send a signal than to do astronomy, but it's the right place to go. Mars is a whole lot further away, and the rest of the planets are farther than that. So you could imagine traveling to the rest of the solar system, and we certainly are going to think about how. So far we're sending robots. We've sent robots everywhere. We could, if we really, really tried, go farther than Mars. But that's hard, and it's pretty dangerous as the way we would do it today. So now I want to talk to you about this discovery of the early universe. So this is a map that got a Nobel Prize for us. When we heard about the expanding universe in 1929 from Edwin Hubble's graph that showed the rate of expansion, the distant galaxies running away from us, it took a little while to get to the calculation that said in 1948, right here in this university, that there should be cosmic microwave radiation left over from those early times, and we ought to be able to see it. Well, in those days, it was too hard to do. Nobody went to look. In 1965, it was discovered by accident. People were working on the space program and trying to start up telecommunications by bouncing signals off of satellites. So that was at Bell Telephone Labs, and they said, well, no, there's a little extra noise in our receiver. What is it? And it turned out to be this. So now we have a map that shows the sky is not equally bright in all directions, but actually has hot and cold spots, which relate to the conditions in the very early universe. When Stephen Hawking saw this chart, he said that was the most important scientific discovery of the century, if not of all time. Thank you, Steve. So why is it important? It tells us the initial conditions as near as we can get to what is the universe like when it was very young. And if you could figure that out, you could say, well, in that case, we ought to be able to predict more or less what happened after that. How did the galaxies grow? How did the black holes grow? How did stars grow in the galaxies? Maybe how do planets grow from the stars and the debris of stars? All those things that we tell you the story of our solar system should somehow connect to this picture. So working out our cosmic history, our personal history, this is part of it. Where did we come from? Where did Jim and I come from? Started there, and let's work out the story. So, by the way, astronomers do something that we can only do. We can visit the moon, we can visit Mars, we can pick up the rocks. We can pick up pieces of the solar system from farther out occasionally. We get lucky, find a chunk on the ground, or even send a probe to get it. Astronomers can travel everywhere, but we can only do it with pictures and imagination. So here's your imagination required to go from that picture to us being here. So what did we see with the Webb telescope? This is one example. That little red fuzzy ball in the upper right corner of this picture is the farthest back in time that we've been able to see. This is a little galaxy. We see it as it was when the universe was only 290 million years old. Tiny fraction of the total age, which is 13.8 billion. So looking almost as far back as we can hope to see the very first things that turned on after the Big Bang. So there it is. We're working on what it is. So we're pretty sure it is a galaxy, and it is not like what we thought it would be, which is one of the cool things about discovery. You build some equipment, you hope to find something, you get a surprise, and oh my gosh, that's not what we thought we would see. I'm glad we built the equipment. We would never have found out without it. And by the way, you cannot make any of this kind of progress without building the equipment, doing the missions that Jim mentioned in the introductions here. Have to build stuff to discover stuff. So there is, as far back as you can see in time, so far. There may be a few more a little farther back in time, and who knows what surprises may still turn up. We've only been running the observatory scientifically for almost 3 years now. We turned it on in June of 2022. Okay, so beginning of the science of the very first objects. We're looking at these objects. This is a place called a We call it the pillars of creation. Because it's a pretty picture. It's actually a place where stars are being born today, inside that cloud of dust and gas. There's a wind blowing from the top right down to the lower left, and you can see how it's ripping shreds into that cloud. There are a few places where you can see stars right on the leading points of the cloud that are just their formation has been triggered in that cloud. Well, why are stars born in clouds of dust? Because gravity has to overcome the gas pressure in order to pull something in. So how do you make the gas pressure go down? Keep the object cold. So the dust makes this possible for new stars to be born there. By the way, there was no dust in the early universe, so the first generations of stars, the first galaxy that I showed you, was formed in a completely different way. So we do not know how that was yet. We're working that out. It's one of the joys of discovery and the stories to tell all of our public to share in our beauteous history of the universe. So there's part of it. Presumably, there are stars being born with planets like ours right in there. And here's an example closer up. This is a star that's in the process of being born. What you see is an edge-on view of the new solar system. Edge-on means there's a lot of dust orbiting in the plane of the orbits of all those future objects, planets that might be in there, where it says disk and dark lane, that's the future planets growing in there. The star is actually hidden from us. You can see that it's sending out jets of material north and south, up and down. And there's maybe even a spiral structure growing in there. We do not know really how this works, but we got a picture. So we are, of course, what do we do next? We turn on our imagination. We say, okay, I've got a computer program. I will simulate this, just like we simulate the weather here on the Earth. We simulate the formation of new stars with planets and dust and everything that's orbiting around them. So we're learning. We will be able to tell you sometime, a few more decades, maybe a little more certainly, how something like the solar system could form. Now, the solar system is unique as far as we know. That's interesting. So how do we know? Well, this picture didn't turn out quite so well as it was, but then how do we know about other planets? This is one technique that's very powerful for us. If you wait long enough and stare at enough stars, sometimes they'll blink because a planet goes in front of the star. And I even met a student who found one of these for his astronomy class homework. So it's not that impossible to do, but we've done it systematically. We've got thousands in the catalog. And what we especially do with the Webb is we know when it's going to happen. We point our telescope at it and we say, okay, how much light is going through the atmosphere of the planet on its way to our telescope? We spread that out with a spectrometer at the different colors, the different wavelengths, and do the chemistry on that information. And so we can now work out, are there planets out there that have atmospheres? And do they have chemicals in them that are interesting to us as possible signs of life? So yes, so far we've been able to analyze large planets, Jupiter-class, Neptune-class sizes, and they do have interesting chemistry. There was a big hoo-ha lately about a planet that has an unusual molecule called dimethyl sulfide. Some people said, well, that's a sign of life. Well, probably not, but it is formed here on Earth by living things. So that get everybody excited. But that planet is a hot planet, so very unlikely. It's got hydrogen and water and carbon dioxide and methane and things like that. Probably no surface under that, so not another home. Mars is possibly like home, which makes it super especially interesting. So let me just wrap up here and say there's much to find out. I'm really interested in the Mars program because it lets us find out the answers to things we could never do just by imagination. We could go pick up a rock like he has and say, I see that, I analyze it. Maybe we'll find one that has microbes in it. Maybe they're alive, maybe they're dead, but there's something. This is the first chance we really have to do that. So I'm hoping for the best.
Thank you, John. I don't know about the rest of you, but I would just sit up here on the carpet at their feet and just listen. Because to me, just what we've heard, which is such a tiny fraction of what has been delivered by the dollars that this nation has put into space science and space exploration, seems to be worth it on its own, just for the sense of wonder that it generates. I mean, speaking for myself, I'm willing to put $2 or $3 a year into making sure this continues. I got a question, and by the way, because we got a little bit of a late start, I've been told we can take a couple of extra minutes here. I'm also almost embarrassed to ask because it's such a cliche question now, but we are in difficult times, budget-wise. USAID is gone. The Consumer Financial Protection Bureau is hanging by a thread. Medicaid, NASA's sister organization, NOAA, lots and lots of priorities. How do each of you answer people when you get that question that all of us get in this business? Why should we be spending money out there when we have so many problems here and so little money to take care of them? Jim?
Well, from my perspective, we're just becoming aware of life on Earth's fragility, in the sense that when we look back at our history, major changes have happened on Earth that have been climate change, have also been the fact that the Earth goes through a variety of different phases. For instance, there's near-Earth objects that we're now becoming aware of. You know, our orbit is not really a very good orbit. It turns out it's full of maybe 60,000 or more near-Earth objects, many which cross our orbit. They're going to hit us. It's not a matter of if, it's only a matter of when. And that realization only occurred when we really recognized features on Earth that were impacts, related that to what we now know about the moon, dominated by impacts, and therefore, what's our history of going through mass extinctions. So all those things are related, and it's because of the orbit that we're in. In addition to that, you know, as the sun moves around the galaxy, it's going through a variety of molecular clouds. This changes the heliosphere. Now, the heliosphere has been a wonderful protective globe around us, but there's perhaps a time when we've gone through molecular clouds for which that has shrunk to the point which has popped the Earth out into interstellar space, where we receive a major increase in cosmic rays. And so we're just becoming more and more aware of the history of the Earth and how it has survived and how it will have to survive into the future, with humans being the dominant species. So that awareness really comes from space. And then in addition to that, of course, we monitor the Earth from space. You know, satellites roll over countries, look at how much food is under cultivation, and can estimate, you know, are you going to export or import food by the end of the year? So there's so many benefits by going into space. We've got to have it. Our future is there, or we won't survive.
Space science, science about Earth from space, enlightened self-interest. So let's get Neo Surveyor out there, which is, you know, that's why the dinosaurs all died. They canceled their infrared satellite that was looking for those rocks. Jim Garden.
Well, I was just going to say, Matt, first, it's a privilege to do what we've had the joy of doing. And really, that's, you know, that's a privilege the taxpaying public have given us. So, you know, it's to be cherished. And so times change with investment strategies. You know, we all have 401ks or whatever. It goes up and down. But I think for me, there's a couple of things that build on what Jim said. First, we live in space profoundly. And this universe is collisional at every single scale. We don't even know the energetics of the most recent impacts of asteroids in Earth history. We do not. Some of them we could be missing by an order of magnitude, which may have had more perturbations in the history of what we call life. So that's one thing. The other thing is, by doing what we've done for the last 60 plus years, we've established a situational awareness of our place in space. And that transcends everything we've done, whether it be Mars or the bigger universe, as John was saying, what Brittany was saying. And that situational awareness gives us the ability to understand aspects of that destiny question that John was asking. And so whether we know everything, we know a lot. You looked at that picture of Olympus Mons. There's a 3-kilometer cliffside around this thing. What the heck? Well, it turns out a lot of ocean island volcanoes have the same thing. Go off the coast of Hawaii, just under the water, and there's a huge one. We didn't know that. But we went to Mars and we figured that out. And so sometimes by that situational awareness of comparison, however we use it, samples from the asteroid Bennu, things in deep space that John was talking about, how solar systems form. Seeing solar systems in other states of habitability in time, because they haven't progressed to the state ours is in the places we think it had been habitable or is habitable, is a profound possibility. Those things will ensure our destiny. And the final thing I'll say is, we all like to run the numbers, okay? So if you run the numbers through the eyes of the brilliant economists at business schools, and you run them and you say, so what's the force multiplying value of 60 years of this investment? Just take the robotic investments. You can slice it and dice it in many different ways. But if you use just simple deep learning, looking at 60 years, you see the numbers are 4 to 5 to 1 for every invested dollar. And we can turn it around and make it other things. But those investments come in intangible ways and intangible ones. So we can now land where we want to land on Mars, good to a kilometer or less. Not the size of a basin on Mars, but that's going to enable those steps that we are so anxious to take to get humans there, to return samples, to look for extant life or not. Those things are enablers. And so this legacy of engineering and technology, I call it the T's, technology, engineering for applications of science for exploration. The big T's has worked. And by being leaders in that domain, we know more about where we live and how we live, and we know how to discover some of the things that you heard from John and others. So to me, that's fascinating. It's an investment that's to be cherished. I hope we can continue.
Not $1 has been spent in space, unless it was between a cosmonaut and an astronaut playing poker on the ISS.
That's true.
But Brittany?
Yeah, I think there's kind of three things. We've talked a little bit about the finances, as it makes good financial sense, and we tend to think about it as that we do this now because we're so successful. I would argue that we have been so successful because we chose to make these investments when we made them. This is a backbone of our economy. Research and analysis, fundamental research in this country is responsible for like 10% of our GDP, even though it costs less than 1%. It's a huge return on investment. So if you just want to be self-motivated, you don't want to take the backbone out of the economy. But I think it's more than that, because we crawled out of the cave, right? That's the whole identity of humankind, is that we're motivated by curiosity. When you don't know what you're going to find, you won't know how to use it, but we figure out a way. And so those fundamental investments are really linked together in how we see ourselves and in where we see ourselves going. We have the chance to save ourselves. We talked about asteroid impacts, to go looking for the killer asteroid, but we also have a chance to see our own planet and to make changes that we need to make in order to save ourselves from a major disaster that's part of our technological advancement. But I think the other thing is that it's just inspiring, right? At the end of the day, I don't get up out of bed because I need to make a 9 o'clock meeting. It's the results that are coming from that, right? Not everyone who studies science ends up as a scientist, but they learn techniques. Many of my graduate school colleagues are bankers, are coders that are working on safety for humankind, that are working on health innovations. Innovations in looking and searching for life through astrobiology are related to discoveries in cancer and to medication. So these interconnected nature of science and discovery is who we are as people and is a part of us financially and as our motivation. So I think you can't really pull those things apart from each other, and they provide people kind of direction and an inspiration, right? That's a personal engine as well as an economic one.
John, anything to add?
Yeah, my perspective is what we do as scientists and as scientist engineers as part of our national science program has been the key to national prosperity. Senator Mikulski used to say it was always about jobs, and I still think so. When we decided as a nation that we were going to go to the moon the first time, Jack Kennedy was really worried that it was going to bankrupt the country. Well, it made the country prosperous. So all the technology that we have today grew out of the immense investment that we put into the space program. The government's the customer that will pay whatever it takes to do the job. And in 8 years from the speech at Rice to landing on the moon, 8 years we did that. That was an immense investment. It cost us a lot, and it gained us a lot. We gained us national prosperity and national security all at once with the space program. It wasn't a fundamental science research program. It was a huge engineering job, and we got them there, and they came home. And I'm so impressed that we did that. I think we should keep on doing that.
Hear, hear. I'll just throw one more at you, because I don't think we should go beyond about 5 minutes over. You're all so passionate about your work, your research, and why this is so important. And there are hundreds, thousands of other scientists who could also have been on this stage expressing the same feelings. What more should scientists themselves be doing to communicate this to the people who matter, which is the folks who vote and the people up the street here who decide what bills get passed and what budgets get approved?
Well, from my perspective, it's all about communicating the science. Science isn't done until you communicate it. Scientists have science meetings to communicate science that they're doing to others, and that spurs new ideas, new science. But going beyond that is absolutely critical. Talk to your neighbor, get them excited about what's happening. Go to local schools. The inspiration that occurs is unbelievable. I had a podcast called Gravity Assist. I interviewed 100 scientists and engineers, and I said, what was those things that got you so excited, that enabled you to change your direction from whatever you were doing to become the scientist you are today? And every one of them came up with inspirational ideas, whether it's talking to an astronaut, seeing a program, reading a book, having parents that are excited about the science and getting you excited. Those are the things that we have to be able to think about doing more of.
I see Chris over there. He wants us out of here, but please, we'll take another few seconds, just a few seconds each. John?
Yeah, I
and then
just
we'll come
wanted
back.
to say that science isn't the only area that's being threatened by cuts in the budget, and all of them matter to all of us. So health, retirement, Social Security, all those things matter to everyone, and the government has a major job to maintain those. We put those in place for a reason. It was a national consensus for like 50 years, and we like it. So we should keep on going all of those things, and that's my feeling. We're not especially just complaining about or worrying about science. The whole nation has got a decision to make.
It's great nations. It's not about this or that. It's this and that. Jim Garvin, I'll come back to you in a moment, Brittany. We'll let you wrap up. Jim?
So I think it's also the messaging in what the engineering has given us. I think it's, John, we all were saying that indirectly. The quest for the science pushes the engineering. And for me, in communicating that, I think of the IT revolution we're in and the possibilities. We're in a digital exploration era now. We weren't at the early Apollo. We barely were. I mean, we were, I guess, to be fair, even though some certain computers failed on terminal descent and things. So those are some of the byproducts that we can communicate, because we take it for granted that the compute power in our cell phones and things like that now can be projected into space. Space is the place to push those boundaries and to communicate that. That is going to be an economic engine too, to the backbone point. And I don't think that's communicated enough, because every time I think of rovers on Mars and I told the stories, it's the engineering successes where people said, well, that can't be done. They told us we could not fly a laser altimeter to map Mars. It seemed to work. I mean, I think people are pretty happy with it. And gee, it did well on the moon. We prepared the place on the asteroid Bennu. I mean, so those who say not, I think I've always found in my experience, the engineers can make it happen. And that story is, it's the American ingenuity story, the world ingenuity story, really. And, we should talk about that and communicate it as Jim said. So thanks.
Brittany, you get the last word.
I think we need to remind people that we're also talking about people, right? We're talking about scientists and engineers and people with kids and people who are teaching colleges and people who are building things and people who are building teams. This is a human endeavor, and it's one that's been distinctly American and distinctly motivational. NASA's the best brand in well, the universe that we know at least, and that's because of what it did for everybody. So it's this call to action that really is very human, and it's done by people. Every one of those dollars spent on the space program or in fundamental science in any of the government agencies is one that's spent on the jobs of people and on things that are going to make everybody's lives better. So removing humans from the equation, we can't separate the science from the scientists, and we shouldn't want to do that because it really is amazing that a bunch of self-organizing chemistry got up one day and said, who am I and where am I going?
What is it Carl said? Carl Sagan, we are a way for the universe to know itself. Please help me thank these 4 inspiring leaders. We are way over. And it is my pleasure now to introduce a special video statement that we have received from Democratic Senator from Maryland, Chris Van Hollen.